Put your hand flat on the nearest surface and press down. Feel that? Solid, real, absolutely, undeniably there. Now here's the strange part. In your entire life, you have never once actually touched anything. Solidity feels like the most certain thing in the world. The floor holds you up. The cup doesn't melt through your fingers. Things are just there. But stop and ask a question almost nobody asks. What does solid actually mean? Why does full feel full? To answer that, we're going to take one long journey, shrinking down through your skin, past your cells, all the way into a single atom. And by the end, you'll understand why you've never truly touched a single thing, and why that's not sad at all. It might be the most beautiful thing about being alive. Because this isn't just about tables and floors. It's every handshake, every hug, every time someone you love held your hand. All of it hides the same secret. So let's go find it. Down we go. We start at your fingertip pressed against the table. Zoom in, and the smooth surface breaks apart into ridges, then into cells, a whole living landscape. Keep going, inside one cell, past the swirling machinery of life, until we reach the thing everything is built from, a single atom. Here it is, at the center, a tiny, incredibly dense core called the nucleus. Around it, a cloud of even tinier electrons. And more than a century ago, an experiment revealed something about this picture that should have been impossible. In 1909, physicists fired tiny particles as sheet of gold foil. Almost all of them sailed straight through, as if the foil was barely there. But a rare few bounced sharply back. Rutherford realized the atom must be almost entirely empty space, with all its mass crammed into one minuscule core. But how empty is empty? You may have heard that if the nucleus were a marble, the atom would be the size of a stadium. That comparison is actually way too small. For hydrogen, the atom is about 60,000 times wider than its nucleus. Blow that nucleus up to a marble at the center of a field, and the electron would drift roughly 600 meters away. One marble, in a space more than a kilometer across. A whole town, empty, wrapped around a single grain. Run the numbers on volume, and an atom turns out to be more than 99.9999% empty space. And you are made of these. You are almost entirely nothing at all. Which leaves us with a maddening question. If you're mostly empty space, and the table is mostly empty space, why don't your hand and the table just pass straight through each other? First, forget the picture of electrons as little planets circling the nucleus. That's a myth we teach kids. Electrons are more like a fuzzy cloud of probability, a smear of where they might be. That matters because a cloud has no hard surface. There's no solid shell to knock against. So when two atoms meet, what actually stops them? Here's the first reason. Every electron carries a negative electric charge. And like charges repel, push two of them together and they shove back, harder and harder the closer they get. So as your hand's electrons approach the table's electrons, they meet an invisible wall of pushing. Nothing has touched, but you feel resistance. And this is where most explanations stop. Touch is just electrons repelling, they say. The end. But that answer is incomplete, and the real story is stranger. Because it turns out electric forces alone can't actually hold matter apart. A theorem from 1842 proved that charges pushing and pulling can never sit in a stable balance on their own. Something else has to be keeping you solid. That something else is one of the deepest rules in physics, the Pauli exclusion principle. And it isn't a force. It's a rule about what nature simply won't allow. The rule is this: no two identical electrons can ever occupy the exact same state at the same time. Think of it like seats. Every electron needs its own, and none may share. So when you try to squeeze two objects together, you're asking their electrons to crowd into seats that are already taken. Nature refuses. Forcing it costs a staggering amount of energy. That refusal is why matter takes up room at all, why it can't be endlessly compressed, why your hand stays a hand instead of collapsing into a speck. So which one really makes you solid? The electric push or the quantum rule? The honest answer is both. It's not a competition with a single winner. The electric force is the push you actually feel. The Pauli rule is why the clouds refuse to merge and why matter can't be crushed. Take away either one, and the world you know falls apart. This isn't a hunch. In 1967, two physicists, Freeman Dyson and Andrew Leonard, set out to prove it with pure mathematics, reportedly with a bottle of champagne riding on the outcome. What they proved is breathtaking. Without the Pauli exclusion principle, ordinary matter wouldn't just soften. It would collapse into something vastly denser. The ground beneath you, the book in your hands, your own body, all of it shrinking to a fraction of its size. Everything you've ever known holds its shape because electrons refuse to share. This is why you don't sink through your chair. Gravity is pulling you down right now. But the electron clouds of your body and the seat refuse to interpenetrate, pushing back with an equal force. Press harder, and they push back harder. It's not a wall of stuff. It's a self-adjusting force field, holding you a hair's breadth above everything you sit on. And we can watch what happens when this force loses. In a white dwarf star, gravity crushes atoms so hard that only the Pauli rule, a pressure from electrons refusing to share, holds the whole star from collapsing. Push further into a neutron star, and gravity wins even that fight. The result is the most rigid matter we know of, by some measures far beyond diamond. The same rule that holds up your chair holds up the corpses of stars. So come back up now, out of the atom, up through the cells, back to your hand resting on the table. Everything looks solid again, but you know the secret now. If your electrons never actually reach the table's electrons, what exactly are you feeling? Force. Tucked inside your skin are tiny sensors that fire when they're pressed and bent. That pressure is transmitted electrically across the gap. They send a signal to your brain, and your brain gives it a name. Touch. Now, let's be honest, because the truth is more interesting than a slogan. There are times things really do get close. Push atoms together with the ferocious energy inside a star, and their nuclei can fuse. And in chemical bonds, electron clouds genuinely overlap and share. So, you never touch anything isn't a cosmic law. It's a statement about everyday life, about pressing two separate objects together, where their surfaces never merge. And at that scale, it holds. Which brings us back to the beginning and to something quietly astonishing. Between your hand and everything you have ever touched, there's always been a gap that never fully closed. And yet, the warmth was real. The pressure was real. The feeling was completely, undeniably real. Nothing about the gap made any of it less true. So think of every hand you've ever held, every hug, the touch of someone you love. None of it was your atoms merging with theirs. It was your fields reaching across a tiny gap and answering. Connection was never about the stuff arriving. It was about the force passing between. And that's why this was never a sad story. The gap doesn't make touch less real. It makes it a small miracle that, across all that empty space, we can feel each other at all. You are almost entirely empty space, held together and held apart by invisible rules older than stars. And still, somehow, you can reach out and feel the world. That's not a trick. That's a wonder. So the next time you hold someone's hand, remember, you're not touching them. You're reaching across a gap that has never once closed and feeling them anyway. If a hidden truth like this just changed how you see something ordinary, subscribe, because curiosity has no limits and we've barely started digging.